So today we'll be going over uh, some EMC problems on number theory. And before that, I'll just share my screen. Sorry, my iPad's just loading for a bit. Can you guys see my screen? Just let me know if you can't. All right. So we'll be going over some EMC problems. And the first problem is just a sec. Let me find it. Okay. Yeah. So the first problem is, what is the tens digit of 7 to the 2011? And I believe that we covered some of the concepts related to this last class, but I believe this is a good problem that'll help us review what we learned last class and build on it, right? So what is the tens digit of 7 to the 2011, right? And like, to start this problem, what can we do in the beginning? Like, if just to jog some uh, memory of what we did before winter break. All right, so I'll start. Basically, what you want to do is you want to remember that. So if the problem says tens digit, the tens digit is usually an indication of mod 100, right? So a number x mod 100, because that'll give you the last two digits of that number. So something like x mod 10 will give you the last digit, right? That's what we learned last time, right? But something like x mod 100 will give you the last two digits, right? So you get the last two digits, and for the tens digit, I'll just take the first digit of those two, right? And so basically, we can translate this problem into mathematical terms, such as, and basically what we say that the problem is asking us to do is find 7 to the 2011 mod 100. And what's that equal to, right? Um, and so does anyone have any ideas on how we can start? All right. So, um, usually a good way of thinking about this is, since this problem involves mods, we can think about patterns that evolve when you look at a number mod something, right? And then we can usually build on that pattern and find what we're asked to do, right? So I'll just go ahead and find 7 to the 0 mod 100, which is 0 1, right? Because 7 to the 0 is 1, so it's just 0 1. 7, so my bad, 7 to the 1 mod 100. 7 to the 1 mod 100 is 0 7, right? 7 squared mod 100 will give us 49. and 7 cubed mod 100. This you usually need some mental math to do. But I'll just save you all that time here. It's 343, so the mod 100 will involve taking the last two digits, which is 43, right? And so now that we kind of established this pattern, um, let's go ahead. So I believe this is the last one. 7 to the 4 mod 100 will give us, so 43 times 7, which will, because also this is something else that we should basically learn, is that um, you can basically, you don't have to, so 7 cubed mod 100, so 7 cubed is 343, right? But to find 7 to the 4 mod 100, you don't have to multiply 7 cubed times 7. Obviously, that's a lot more work. What you can do is you can take this mod and multiply by 7 to get the next mod. So basically, what I'm trying to say is if x mod 100 is some number, say y, right? Then nx mod 100 is ny. It's just the constant times the y. So we can just multiply 43 by 7 to get whatever mod 100 we need. So 43 times 7, I'll save you all the math there again, it's 301. And so we need the last two digits, which is 01. And so now we need to break this 7 to the 2011 up into bite-sized pieces so that we can look at the mod 100s. Obviously, that's a lot more that, because we don't want to deal with 7 to the 2011 and try to find patterns and all that, because it's just way too big of a number. Then also we're dealing with mod 100s. So um, basically, we see that we want to make this as easy as possible it is for ourselves. And so we see that 7 to the 4 mod 100 is 01. Wow, 7 to the 4 mod 100 is just 1, right? So why not see what the uh nearest multiple of 4 is to 2011? Because the nearest multiple of 4, 7 to the 4, is just going to be 01, right? So what I mean by that is, so 2011, the nearest multiple of 4 to that, which is less than 2011 obviously, is 2008, right? And that is 7 to the 4 times to the power of 502. And then we see that from 2008 to 2011, you need three more, right? So 2008 plus 3 is 2011. And so to get from 7 to 2008 all the way to 7 to 2011, you need times 7 cubed. And this is what we need to find the mod 100 of. Right? So far, this makes sense, right? And so basically, we can break the mods up into 7 to the 4 to the 502 mod 100 times 7 cubed mod 100, right? And so 7 to the 4, so let's look at this first. This is easier. This is just 43, right? Because 7 cubed mod 100 is 43. But 7 to the 4 to the 502, it's going to be much easier because we know what 7 to the 4 mod 100 is, right? That's 1. So basically, this is another property of mods, which is that you can, if you want to look at this complicated exponent mod 100, you can take the mod into the base of the exponent. What I mean, and that'll just give you the same thing, because actually I'll just let you guys figure out why this is, but this is basically related to what I showed right here. And so you guys can kind of try and see why that's true, right? In your own free time, as this is a very good exercise if you want to get some practice dealing with mods. And so going further, that's 7 to the 4 mod 100 to the 502. Well, 7 to the 4 mod 100 is really easy. That's the whole point of why I tried to get the nearest multiple of 4, right? It's just 1. So 1 to the 502 times 43. Well, 1 to any number is just 1, right? So it's just 43. And so we have the tens, so we have the last two digits of 7 to the 2011. But what we want is the tens digit. Now don't be and now you see the AMC has been very tricky with its answer choices because it's also put 3 here. But remember, the tens digit is always the the first number out of the last two digits. This is the ones place. So the answer we want is D, 4. Does that make sense? Um, yeah, feel free to ask any questions in the chat. Man, I'm sure we'll get to it later. All right. Um, so this is the next problem. When um, 1999 to the 2000 is divided by 5, what's the remainder? And so I'll let you guys think about this problem because it really builds on the like a lot of concepts that we covered previously. Well, okay. So this is gonna build on this concept, which is that if you have say x to the n mod I guess y, right? You can also say that's x mod y to the n, right? And why this is true again, um, you guys can figure it out, and it's a very good exercise if you want some practice with mods. But basically, what we want to notice here is when this number is divided by 5, the remainder is. So we want to first translate the words into math, right? So if it's asking us a number divided by 5 and it wants the remainder, what the problem is basically asking us to do is find this number mod 5 because modding anything will give us the remainder when the number is divided by uh, 5, I guess, right? Um, so how can we start here? Is there something that we noticed, or just any initial thoughts or something like that? No. Okay. So what we can generally notice is when we try to do things with mods, we want to make this easy for ourselves, right? Because we can look for a pattern um in like say the numbers. We can look for a pattern because I'm sure if you have some 9 to the something, there is a pattern, and I encourage you guys to work through this problem the other way. I'm gonna show you what I'm gonna show here is a different way, but the other way considers working with numbers that have a base of 9 and an exponent of something else. And as you'll see, so 9 to the 0 is 1, 9 square 9 to the 1 is 9, and then so on. As you'll see, there is a pattern that emerges between all the numbers that are 9 to the n, right? Mid the last digit, right? So there's going to be a pattern in terms of the last digit that you guys can try to find and then solve this problem that way when divided by 5, right? But what I'm going to show here is a much faster way to do this using mods. And another reason why mods are such a powerful technique to use when it comes to solving AMC8 number theory problems, and really um, even beyond that, in the SAT or maybe the AMC 10 and 12 as well. So um, if you guys are planning to take that, mods are something that's really important. So here's why, right? So 1999 to the 2000 mod 5, we have to find that. But what I can also you know do is uh, I should add this. Right. Okay. So what I should do is I should use this property, right? So I have this big number to the big number mod 5. Let's see 1999 mod 5 to the 2000 mod 5. Well, let's try to find that out cuz I'm sure dealing with 1999 to the 2000 mod 5 is going to be very long, and usually not the time's not worth it in the MCA. But this method allows us to make the problem much easier, right? So there's so when you're doing mods, you can have positive mods and you can have negative mods. I'm not sure if we covered this earlier on, but I'm just going to show you guys some examples. So 5 mod 3, you can usually write this two ways, right? You could either write this as being congruent to 2 mod 2, right? 5 mod 3. You can either say this is congruent to 2, or you could say, or alternatively, you could say that this is congruent to negative 1. Why this is, I'll show you that. Um, because really, I'm just gonna write the mod 3s, but when I emit the mod 3s, just remember that there is a mod involved. But why this is because when you get to 5 mod 3, there's two ways of approaching 5, right? From multiples of 3, closest multiples of 3. So you can get to 5 from here, which is a jump of plus 2, so it's 2 mod 3. So 5 mod 3, when you go from 3 to 5, is obviously just 2 mod 3, because uh, 5 divide so the number that divides like perfectly into 3 is 3 itself, right? And 5 is 2 away from that, a positive 2 away from that, so the remainder is just 2. But what you also have to realize is that sometimes this makes this as here, this will make a lot of problems much easier, is you can have negative ones, right? So from 6 does divide 3 perfectly, but the remainder from 6 to 5 is of negative 1, right? Because you have 6 and you subtract 1 and then you get 5. So the remainder when you divide uh, like so the remainder when you divide 5 mod 3, you've usually encountered positive remainders up so far, but when you deal with mods, there can be negative mods as well as positive mods. So you can either have 2 mod 3, which is when you get grow from a lower number to the number that you want, and there is also negative mods, which is when you go from the higher number and you go to the number that you want in the middle. So 5 can be either 2 mod 3 or negative 1 mod 3. And why I covered this is going to be uh, really helpful here is because we want we want 1999 mod 5, right? How can we write this in terms of both positive mods and negative mods? And which one's easier for us to deal with here? All right. So, uh, so 1999 mod 5, there's two ways of approaching 1999 again, right? You could either go from 1995 to 1999, which is a jump of positive 4. So if you have 1999 mod 5, you can have that. So you can have 1999 is congruent to 4 mod 5, right? Perfectly logical, reasonable, right? And you could just say that this is 4 to the 2000 mod 5. But as we will see, the other way is much easier, and it'll get us to the answer much quicker. Because you could either have 1995 to 1999, but as in the 356 case here, there is also a number that's larger than 1999, which is a perfect multiple of 5, but that's gonna give us a negative mod, right? And that number is 2000, right? Because uh, both 1995 and 2000 are divisible by 5. 1995 to 1999 is 4 positive steps. But from 2000 to 1999 is just negative 1. So 1999 is congruent to 4 mod 5 or negative 1 mod 5. Why? Because you could go from a perfect multiple of 5, you could go either plus 4 steps and get to 1999, which is true because from 1995 there's plus 4 steps. Or you could backtrack one step. So from 2000, you could go to 1999, which is negative 1, and you could write this as being negative 1 mod 5, right? So now we see that this is equal to 4 to the 2000 mod 5, or it could be equal to negative 1 to the 2000 mod 5. And look at how much easier that is, because negative 1 to the any number is either going to be negative 1 or positive 1. But 2000 is an even number. So what do we know about negative one to negative one to an even number? It's always going to be positive one. Negative one to an odd number is going to be negative one to negative one to an odd number is going to be negative one, like as is expected, right? So we go back. So we see that 1999 to the 2000 mod 5 is equal to 1. And so our answer is going to be B here. Did that problem make sense to everybody? Please feel free to ask questions, because if I'm not making sense, then you can send your questions in the chat, and we'll get to it later. Right. And so this is another reason why mods are very helpful for dealing with mod 5s um and like really any other problem, because if we didn't have the knowledge of mods, right? We could have done, say, so we could have tried to analyze the last digit of 1999, which is 9, and you could have tried to find a pattern between 9 to the 1, and then, or 9 to the 0, 9 to the 1, which is 1, and then 9 to the 1, which is 9, and then 9 squared, which is 1 again, because 81, the last digit is 1, and then so on. And then you could have tried to deal with that mod 5 or some mod 5. But for me, honestly, this way is much easier, because if you just look at the number, you can see that 1999 mod 5, if you have knowledge of mods, you can see the 1999 mod 5 immediately, that's equal to negative 1 mod 5. And so if negative 1 mod 5 to the 2000, well, negative 1 to the 2000 is just 1, so it's just 1 mod 5, right? And that's how easy it can be if you know mods, compared to if you were just, I don't know, just trying to find patterns between last digits and so on, right? And I believe I believe there was one more problem that I wanted to cover. Um, I'm just gonna pull that up real quick. Yeah, this one. So, um, this problem says Mrs. Walter gave an exam in a mathematics class of 5 students. She entered the scores in random order into a spreadsheet, which recalculated the class average after each score was entered. Miss Walter noticed that after each score was entered, the average was always an integer, and so the scores listed in ascending order are these. And so, what was the last score Mrs. Walter entered? And so, this doesn't use your knowledge of mods, but again, this is a very useful problem in number theory that you should know how to do, right? So, I'll show you guys two ways here. And there is a slightly slower way and there's a faster way to do this. But basically, we have a class of 5 students. So I don't know. So let's say A, B, C, D, and E, right? And so what she says, or what Miss Walter says. By the way, this is not necessarily the actual like order of the scores that Mrs. Walter is entering it in. This is just the scores listed in ascending order. So you have to find the order with which Miss Walter entered the score. And so what this problem is saying is that a plus b over 2 is going to be an integer. So, well, a is going to be an integer, and then a plus b over 2 is going to be an integer x. And then a plus b plus c over 3 is going to be an integer, say y. And then a plus b plus c plus d is going to be an integer, or 4 is going to be an integer, say z. And then lastly, a plus b plus c plus d plus e over 5 is going to be some integer, say, I don't know, say n, right? But what we have to realize is that we don't even have to actually look at the order that Mrs. Walter entered the scores in, right? And here's why, because whatever z is, right? Z is an integer, right? So you have a plus b plus c plus d over 4 is equal to z. So what's a plus b plus c plus d equal to? 4z, right? You just multiply both sides by 4 and you get z. By the way, this is me just translating the problem statement into actual mathematical numbers. And so we can say that 4z over 5, or I guess an easier way to write this is uh, E equals 5n minus 4z. And hopefully this made sense, because I'm just trying to save time here, but you guys can actually work through this. And so we have to see that from here, um, E is gonna be 5n minus 4z, right? But what we have to remember here is that we have to find the last score Miss Walter entered. But so if we try to look at that, right? We realize that the last score has to be 80. And here's why. This is because we know that 5n, so a plus b plus c plus d plus e, has to add up to all of these, right? Which is 71 plus 76, which is 148. And then 80 is going to give us 228. And then, oh, my bad. 71 plus 76 is 147. And then 227. And then, so it's going to be some multiple of 5, right? As you can see, a plus b plus c plus d plus e is going to be some multiple of 5, right? I'm not going to actually do the calculation. You can see that. So in order to, so if you add another number and then divide by 5, and if that has to be an integer, then if a plus b plus c plus d was already, if a plus b plus c plus d plus e is something that's divisible by 5, and then if a plus b plus c plus d was also something that's like divisible by 5. We know that E has to be something that's divisible by 5, just in order to keep um, that in that part of the number, that part of the problem statement which says that the um, the uh, the average has to be an integer. Because for the average to be an integer, you have to have the uh, number 80 as the last digit being entered. Um, if I know that was a bit rushed, but if that didn't make sense, please drop questions in the chat, and I'll make sure to answer them to the best of my ability. And with that, Daniel can take over. Thanks, guys.
All right, cool. Okay. Yeah, okay, cool. My audio's on. Thanks, Sid, for wrapping up our number theory problems. I guess for now, that will be the end of our number theory unit for our MCA session classes. Obviously, we're going to send out more mixed practice as we go along. But today we're going to start a little bit of geo. And today is just going to be the basics. We're going to be covering angles, especially angles within a parallel line setting and triangles. So with that, let's just get started. All right, so I'm going to write just right next to the space where Sid wrote, just because like it was a little bit rushed for me. But anyways, so today we'll be going over basically what angles are, some basic properties of angles, some basic triangles, and then we'll be also covering some MCA problems, which I'll be putting on the Miro, as I go along. Okay, so let's just talk about angles really quickly. So basically, like, what is an angle? Well, if you imagine, let's say, if you imagine a line like that, say, starting from a point A, right? A point is just a point; it's just a space, and it's just like basically like where you're standing in space, just a point. And so if you have a ray going from A, let's say in that direction, and you have another ray going in that direction, um, and you just consider whatever this is. So basically, like an angle is a really good way of thinking about how far apart are two lines from each other, basically. And so if we call this if we have points B on this first line and C on the second line, we're going to say that this angle, so the angle formed is going to be called angle BAC. So you just basically the notation here is that you're going to start from a line on a point on any line. So we could just call it B right here. And we're going to go to the vertex. So A is the vertex here, which is basically where the angle kind of like starts, where the two lines meet, and then go to the other point on the other line, which is C. So we just call this angle BAC. And so we can also call this angle A. And so in certain settings, angle A could actually be this other angle right here going around. But again, in this specific context, since we're referencing an acute angle, we're just gonna call this angle A. So these are two different ways to call this angle that you see depicted right here, angle BAC and angle A. And so now, obviously, you can form many types of angles with these. And so let's just think about the different types of angles that we can even form. And so let's just start with like the angle BAC, right? So the angle BAC, this is my best attempt to copy over the angle, but obviously you can see that the angle makes like a V shape, right? It doesn't. It's just like a really small angle, and so we call we generally call these types of angles an acute angles. So this is an acute angle, and before we even get into degrees or stuff like that, I'm just gonna draw the other types of angles. And so if one angle is perfect, if one line is perfectly horizontal to another line, and it's going to make like a T shape, and we'll see what exactly that T shape means in a sec. This will be called a right angle, and we usually denote a right angle with the kind of like a square notation on the vertex. And we also have this angle, which is like a kind of a big angle, right? So this will be an obtuse. If we consider this angle, this will be an obtuse angle. And then we usually don't see this on the MC8, but I'll just cover it just for kicks. So this, sometimes we can even go more than, well, actually, there's one more angle that I kind of forgot, which is just a straight line. And so a straight line is really special. This is called a straight angle. I'm just gonna call it straight, and this is reflex. So if you rotate, if you rotate a line such that, like for instance, if you start from here and then you rotate this all the way here, like that, you're gonna form a reflex angle. Oh, I spelled reflex wrong. Reflex angle. And so those are the basic types of angles. And so now we're going to formally define exactly like what these actually mean in terms of degrees. So the basic idea of degrees is that if you have a full circle, if you have a segment, and you're going to rotate that a full circle like that, that angle is 360 degrees. And so if you rotate this segment about the pivot X right over here, halfway, such that the thing forms a line, right? If you start from this configuration and then just kind of like flip it over, we're gonna have an angle of 180 degrees. And so this tells us that a straight angle is 180 degrees. So any line actually, like if you consider any point on that line, the angle that is formed by the basically like the two rays emanating from that point going outwards is 180 degrees. And so this tells us that if you go more than a straight line, so if you start from like, let me see, if you start from here, you rotate all the way to a straight line, that's 180, and you go more than that, that's a reflex. So a reflex angle is more than 180 degrees. And obtuse, okay, so now the main types of angles that you will see on the MC8 are these three. So you want to really focus on these three. And so the obtuse angle is defined as, well, let's first define the right angle. And so the right angle is exactly 90 degrees. So you can think about it like if you start from here, rotate all the way to a line such that like the original segment and the new segment form a line, and you cut that in half, that's just a 90 degree angle. So you go from basically horizontal to vertical, that's just 90 degrees. And so right angle is 90 degrees, obtuse angle is greater than 90 degrees, and acute angle is less than 90 degrees. So in AMC8 problems, you're going to see a lot of terminology like that. Geometry generally has a lot of terminology, but we're trying to give you like a basic outline of what you should know to understand every problem that you're going to encounter. And so these are the main types of angles. Acute angles are less than 90 degrees. Right angles are exactly 90 degrees, and obtuse angles are greater than 90 degrees. I should also mention that it's greater than 90 degrees, but not a straight line. So technically, an obtuse angle is greater than 90. So if we call this like theta, well, I don't want to complicate things yet. So greater than 90, but less than 180, like that. Because a straight angle is not we don't really consider it as an obtuse angle. So that's just a little clarification right there. All right. All right. So these angles, considering these different types of angles, obviously can have different relationships between them, and some are really useful in our applications that we see in the problems. So, all right. So if we consider a line and a point on the line, let's say P, we call this P, and let's say we're gonna have point A on here, point B on here. These are kind of like arbitrary. We don't actually need to pick like a specific point to be point A and B, but let's just say A is to the right of P and B is to the left of P, and we're gonna draw a ray, like just like that. And then let's say on that ray, distinct from P, we're gonna say there's gonna be a point C, right? So remember what we talked about for a line, right? A line, if we pick any point on the line and consider like the angle that is formed. So like if we pick P right over here, and you're gonna see that this angle is 180 degrees. And that's kind of like by the definition of a straight angle. That's just 180 degrees. And so we can effectively add the angles BPC. So we're gonna say BPC plus angle CPA. And then that's just gonna be 180 degrees. And so that's just one example of angle addition. So when you do problems with angles, you're going to write it using the notation that we previously described, like this. And obviously, some teachers in school may want you to write the angles like with an M at the left of the notation that I introduced to you earlier. But honestly, it's not really necessary. So with that, we can just like ignore it for our purposes, especially in AMC8, because they're on a time crunch. You don't want to be writing M's all over the place when you don't really need to. And so from this equation, we can actually say that this is one of the relationships that we're going to talk about. And so we're going to say that BPC and CPA are supplementary. So what this means is that if two angles are supplementary, they add up to 180 degrees. And they're typically presented in this fashion where these two angles highlighted in green add up to 180 degrees, which effectively forms a line. And so like we're going to also have another notation. Don't worry if you're not catching along with all of this. We're going to have a video, a recap video sent to you by email. So just to cover one last, very important relationship, we're going to consider a right angle. Let's say the vertex is called P again, and we're gonna place points A and B just on the two different rays emanating from P. And so I said that it was a right angle, so we're just gonna put a little box right here. And so if you consider a ray in between, or just cutting through the right angle is another way to think about it. And let's say we're gonna have a point C on here. Again, we can just do the same thing that we did with straight angles. Since right angles are 90 degrees. By the way, this is all by definition. So like all of this comes from the definition that a full circle. So if you start from here, rotate it all the way around, that's 360 degrees. That's basically by convention. And so from that, we know that a right angle is 90 degrees. And so since BPA is 90 degrees, we're going to just say that 90 is equal to the sum of these two again. And so what is that? Well, the top angle is angle BPC. So we're just going to write BPC. And the other angle on the bottom is going to be CPA. And so with this, we can say that BPC and CPA are complementary. And sometimes, but not very often on the AMC, I feel like. But if you're doing math counts by chance, you might encounter supplementary and complementary angles. So this is why you should definitely know the definition of these. And so if two angles add up to 90 degrees, we can say that they're complementary. And so supplementary angles add up to 180. Complementary angles add up to 90 degrees, obviously. All right. So these are the basic relationships that angles, or that have names technically, for angles. And we can actually establish more relationships, but there are going to be a lot of names, I feel like. But the important aspect is to know how numerically the angles relate to each other. So with that, we're going to talk a little bit about parallel lines, which is very similar idea. But I think it's basically the same idea. You just it's kind of like the same idea, and you see what I mean when I say that. So before we get started, two lines are parallel if they don't intersect. Yeah. So if you consider this configuration where let's say the top line is parallel to the bottom line, and we usually denote parallel lines using one or two arrows. I kind of forgot, but basically, let's say I guess two arrows. Like arrows indicate that they're going in the same direction. So since they're going the same direction, they would never meet, and since they never meet, they are parallel. And so let's consider the following angles. I'm gonna do it in green just to make it clearer. So this is angle 1. This is angle 2. This is angle 3. This is angle 4. I'm gonna add this notation just so that it doesn't seem like it's like 2 degrees. This is angle 5, angle 6, angle 7, and angle 8. All right. So this middle line that's splitting the two parallel lines is called the transversal. And so I think that in geometry class, you're going to be taught a lot of names, but the main idea is to see that is to see the following. Angle 1 is equal to angle 5 because they correspond to each other. They're called corresponding angles, like that. Because if you have it kind of makes intuitive sense. If you have like a line here and you just have two lines going in the same direction, like the angle cut that's kind of like in the same configuration, it's got to be the same. And so 1 equals 5. We can also say that 7 and is 3, right? By the same logic, because it's this angle and this angle. And so they have the same configuration. We can say that it's, oh, before I jump ahead, angle 3 is equal to angle 7. And then there's one little property that we can apply here is that if we have two lines intersecting like that, the purple angle is equal to the green angle, like that. So these angles are actually called vertical angles, and I think you should know this. So I'll write it down. And so with that, we can say that angle 5 is equal to angle 7. And so since these two are equal, right? 1 is equal to 5, angle 1 is equal to angle 5. Angle 5 is equal to angle 7. We can actually say that angle 5 is equal to angle 1 is equal to angle 7. So basically all of these are actually equal. So we can actually extend this equal sign. And then with the same logic, we can say that we can just do it with the even numbered angles. Yeah, like that. And then obviously angle 1 plus angle 2, they form a straight line like that. So we're going to say angle 1 plus angle 2 is equal to 180 degrees because they effectively form a straight line. And you can basically do the same thing for the other angles. You know, any two angles that add up, that kind of form a straight line, they can be added up to 180 degrees. All right. Since I'm not going to have much time for theory, actually, you know what? I'm just going to quickly cover triangles. And so triangles, I think I know you all you guys know what a triangle is. So I'm just going to introduce the different types of triangles. So an acute triangle is where all angles, I'm just going to do that. All angles are less than 90 degrees. And so it's going to look something like this, or this, something like that. Right. A right angle is very special. There is exactly one angle equal to 90 degrees. So it's going to be something like this. And an obtuse angle is where exactly one angle is greater than 90 degrees. So it's going to have an obtuse angle like that. Yeah. Okay. And so those are different types of triangles concerning the angles. And so concerning the side lengths, we also have an equilateral triangle. All sides are the same. So it's going to look something like this. And then we use tick marks to mark the angles, the side lengths are equal. We also have isosceles. So an isosceles triangle has one pair of congruent sides, which means that basically at least two of the sides are the same. So that means an equilateral triangle is also an isosceles triangle, since three sides are the same and matches our isosceles triangle definition. So at least one pair. And scalene is kind of where all sides have different lengths. Yeah. And the crucial thing to know about triangles is that the angles add up to 180. So if we call this ABC, triangle ABC, we can establish that A plus B plus C are all 180 degrees. So this is basically the key relationship between the angles within a triangle. And so this is really useful. And let's just look at one quick example to see how this plays in action. So if you have configuration like this, and you're given that these two top and bottom lines are parallel, this angle is 50 degrees, this angle is 60 degrees, and you ask to find, I'm going to extend this line right here. You're asked to find what is this. So what is this? You can say that, well, if we consider this green triangle right over here, remember what we just said, and I think in a future session we should prove this, or we can prove it in a, or we can just prove it, me and Sid, we can prove it in a separate video. But remember what we said about the angles in a triangle. They add up to 180 degrees. And so we can say that if we call this angle, let's say angle X, we can say that X plus 60 plus 50 is 180. And obviously there are degrees, but we usually don't bother putting the degree sign because that's just like kind of annoying. But technically there is a degree sign, so you just should be aware of that. We can obviously subtract 60 and 50 from both sides to get X equals 180 minus 60, which is 120, minus 50, which is 70. And so this angle X is 70. And then look what we just did. The red angle and this green angle, I guess this light green angle will do now, are vertical angles. And so the red angle will be 70 degrees because vertical angles are congruent. As we saw right over here. Yeah, vertical angles are congruent. Basically, they're the angles that are opposite the vertices. All right. So with that ends our session today. I hope you guys learned something new. And so we'll have a section next week. We'll dive deeper into geometry. Thank you guys so much for attending. If you have any questions, email us, and we'll be sending out the handout in the video. Thank you, guys.
Thank you, Asper.
Goodbye.